For part A of case 5.3, how many Spanish-speaking operators and how many English-speaking operators does the hospital need to staff the call center during each 2-hour shift of the day in order to answer all calls? Please provide an integer number since half a human operator makes no sense. So the problem gives us this table, which indicates the average number of calls for each time period from 7 a.m. to 9 a.m. up to 7 p.m. to 9 p.m. So we copy the data into this table: 40 calls per hour, 85, 70, 95, 80, 35, and 10. And then we also look at other data given by the problem. So the problem states that 20% of the calls were from Spanish speakers. So to get the average number of calls of Spanish, we multiply the average number of calls by 20%. So in this column, C9, which is the average number of calls for time period 7 a.m. to 9 a.m., multiplied by 20% gives us 8. And then the rest, which is 80%, would be English speakers. So C9, which is 40 times 80%, that would be 32. We do this operation for each time period. So for example, for the next period of 9 a.m. to 11 a.m., 85 times 20% would give us 17 Spanish speakers. And for English, 85 times 80% is 68. And then to get the number of Spanish-speaking operators and English-speaking operators, let us see first another data that the problem gives us, which is an operator is able to process an average of 6 calls per hour. If we notice the time period is in 2-hour increments, so we calculate the calls per period covered by one operator in here. We take the calls per hour per operator, which is given, which is 6 calls per hour, okay? And then we multiply it by the hours per time period. And that is from 7 a.m. to 9 a.m., there are 2 hours. So that's 2. 6 times 2 is 12. So there are 12 calls per period covered by one operator. And then to get the number of Spanish-speaking operators, we divide or we use the ceiling function of Excel, which is rounding up to the nearest or to the nearest integer, rounding up. Okay, so for the Spanish, we need to cover 8 calls. We divide 8 by 12, as you see here, D9, 8, and then L10, which is 12. So 8 over 12, that is around 2/3. So, but the problem states that we need to provide an integer number. So we use the ceiling function and round it up to the nearest or to the higher integer. So that should be 1. And one Spanish-speaking operator can cover 12 calls, which is enough to cover 8 calls of Spanish-speaking customers. And for English operators, we do the same. We use the ceiling function. 32 divided by 12, that is more than 2. Okay, so we take the next integer by 3. So we get 3. And 3 English operators can cover 3 times 12, 36, which is just enough to cover 32 English-speaking customers. And we do this for each time period. So for the next time period, 9 a.m. to 11 a.m., that would be 2 Spanish-speaking operators, then 6 English operators. And This column represents how many Spanish-speaking operators and how many English-speaking operators does the hospital need to staff the call center during each 2-hour shift of the day in order to answer all calls?
Okay. For letter B and C for case study 5-3, letter B, the learning needs to determine how many full-time employees who speak Spanish, full-time employees who speak English, and part-time employees he should hire to begin on each shift. So we have to formulate a linear programming model of this problem. For the case facts, we have 20% of the calls are from Spanish speakers. One operator processes 6 calls per hour. One full-time employee works for 8 hours a day, 4 hours on call, and 4 hours on paperwork. Part-time employees work 4 hours a day on call, no paperwork, and only speak English. For full-time employees, 2 hours call, then 2 hours paperwork, alternating. So employees speak either Spanish or English but are not bilingual. For the cost per hour shift, $15 per hour before 5 p.m. and after 5 p.m. it's $18 per hour. Full-time employees can begin work at 7, 9, 11 a.m. and 1 p.m. Part-time employees can begin work at 3 p.m., 5 p.m. For letter B, we have to formulate a linear programming model. So for the group formulated this template. So for each shift, it is 8 hours, 4 hours on call shift, and 4 hours on paper shift. So for 7 a.m. to 11 a.m., it is 15 times 4, since every hour it is $15 per shift. Next, 11 a.m. to 3 p.m., the same. 9 a.m. to 1 p.m., 1 p.m. to 5 p.m., 11 a.m. to 3 p.m. Then for 3 p.m. to 7 p.m., it is 2 hours of $15 and 2 hours of $18, since 3 to 5 p.m. is $15 and 5 to 7 p.m. is $18. The same goes to 1 p.m. to 5 p.m. For 5 p.m. to 9 p.m., it is $18 per hour, since it is after 5 p.m. For 3 p.m. to 7 p.m., $66. And for 5 p.m. to 9 p.m., it is $18 per hour times 4, $72. So for the time periods, the group separated the English and Spanish. So for English, these 12s represent the number of calls processed in the hour. Like said in the case facts, every operator processes 6 calls per hour. So since these shifts are in 2 hours, 6 times 2 is 12, so 12 hours per shift. These zeros represent the 2 hours that the operators are in paperwork shifts. So just plot the shifts. Then for the part-timers, they work for 4 hours with no paperwork. So 12 calls for 2 hours and 12 calls for 2 hours. The same goes to 5 to 9 p.m. For the constraints, the formula for this is the sum product of the row of the shift and the number of operators working in the shift for English. Then just drag this down. Okay. For the constraints, these are the numbers that were found in the part A, which is for the English, the 80% that got from the total number of calls in the problem. For the Spanish, we have the time period, then the plot of the number of calls. For Spanish, since part-time workers only speak English, then this is not available for the Spanish speakers. For the formula, we have the sum product of the row and the number of people working, or the changing variable cells. So these are just the same. Then these are also taken from the part letter A, the part 1. Okay. For the changing variable cells, we have the number of people working that are English and also Spanish. Then for the cost, this is just the sum product of the number of people working and the cost per shifts. Same goes to Spanish. And this is just the sum of the costs for English and Spanish. Okay. To get these yellow cells, we have to do the solver. So solver. Okay. So for the set objective, we will be using 2 solvers. For the English, we have the set objective for the English. This is to minimum. Minimization. For the changing variable cells, we have the number of people working. For the constraints, we have the sum products, and change this. Then we have the given for the English, which is the 80% of the total number of calls. And then for the changing variable cells, this will be changed to integer since in the problem that there are no half humans. So these are need to be integer. Click OK. This would be simple linear programming. Solve. Okay. Click OK. Then we have the number of people working for the shifts. For the Spanish, we have to click solver again. For the set objectives, it will be the cost for the Spanish, minimization, changing variable cells are these without the part-time since part-times only speak English. Constraints greater than or equal to add, then changing variable cells to integer, then solve, then click OK. So these are the number of people that will be working per shifts.
Base facts. California Children's Hospital is centralizing its appointment and registration process into a single call center. The call center operates from 7 a.m. to 9 p.m. on weekdays, and the hospital has forecasted call volumes for each 2-hour shift and determined that 20% of calls are from Spanish speakers. Operators can handle 6 calls per hour. Full-time employees work 8 hours but only spend 4 hours on calls, while part-time employees work 4 hours exclusively on calls. The hospital must staff the call center to minimize costs while answering all calls, with the constraint that only one English-speaking full-time operator is willing to start at 1 p.m. So the main problem is staffing the call center efficiently to handle call volumes while minimizing labor costs. The hospital must ensure enough operators are available for both English and Spanish calls during each shift. Additionally, the constraint of only one English-speaking full-time operator starting at 1 p.m. adds complexity to the staffing plan. So to solve this, we input the call forecasts, operator requirements, and labor. Okay. So to solve this, we input the call forecasts, operator requirements, and labor costs into Excel. We create tables for call volumes, operator availability, and labor costs. The decision variables such as the number of full-time English, full-time Spanish, and part-time operators for each shift are set up in cells C11 to C20 as seen on the screen, and these cells are left blank initially as solver will determine the optimal values for this. Okay. So the key formula for calculating the total labor cost is number of operators multiplied by the hours worked and the hourly wage. This formula ensures we account for the cost of each operator type and shift. For example, if we hire 4 full-time English operators at 7 a.m., working 4 hours at 15 per hour, the cost for that will be 240. This formula will then be applied to all operator types and shifts to calculate the total labor cost. Okay, so now moving on to the solver part. In solver, we set the objective to minimize the total labor costs, and the decision variables are the number of operator cells in C11 to C20. The constraints include ensuring the number of operators meet or exceeds call demands for each shift, limiting the number of English-speaking full-time operators starting at 1 p.m. to 1, and ensuring that all decision variables are non-negative integers. These constraints are entered into solver's parameter dialog box as seen on the screen to ensure that the solution will be feasible and meets all requirements. So if we run this, we will get the following staffing plan. For example, we should hire 4 full-time English operators at 7 a.m., 5 at 9 a.m., 8 at 11 a.m. and 1 at 1 p.m. For the Spanish, hire 2 full-time Spanish operators at 7 a.m., 3 at 9 a.m., 3 at 11 a.m., and 4 at 1 p.m. And for the part-time, there will be 10 part-time operators at 3 p.m. and 5 at 5 p.m. So the total labor cost will be 2,760. And as you can see, this plan satisfies all constraints, including the limit of one English-speaking full-time operator starting at 1 p.m. and ensures that all calls are answered efficiently. Okay, so for part E, the key formula is for calculating total labor cost. Total cost equals number of operators multiplied by hours worked and hourly wage. This formula ensures that we account for the cost of each operator type and shift. For example, if we hire 7 bilingual operators at 7 a.m., working 4 hours at 15 per hour, this formula will be applied to all shifts to calculate the total labor cost, which is 1,824. In the solver, we set the objective to minimize the total labor cost, which is this one. And the decision variables are the numbers of operators in here, cell C11 to C16. And the constraints will be ensuring that the number of operators meets or exceeds the total operators needed for each shift, and that we ensure that all decision variables are non-negative integers. Okay, so after running the solver, we get the optimal staffing plan, which is hiring 7 bilingual operators at 7 a.m., 5 at 9 a.m., 5 at 11 a.m., 8 at 1 p.m., 3 at 3 p.m., and 2 at 2 p.m. And the total labor cost is 1,824.
All right. Now let's tackle the problem of part F, which says that if all employees are bilingual, how many full-time and part-time employees should Lenny hire to begin on each shift to minimize operating costs while answering all costs, or all calls rather. And for this one, we'll also have to create a linear programming model. So here are the case facts that we know and that we have also applied in the rest of our problems. And so for this problem, the amount of Spanish and English speakers would not be relevant. So we'll be taking these as the average, total average calls for each of these time periods. To easily be able to demonstrate this, I've created a time period covered by shift, each of these 2 hour shifts. So it'll be easier to um, picture their shift. So right here are our daily costs per shift, and this is calculated by um, many hours will each operator spend taking calls. So that's um, 2 2 hour shifts, and um, in this program right here. So the formula we'll be using for how many calls can be taken in these shifts are a sum product of each of this and the number of operators to be working in those shifts. So we have a 7 to 3 p.m. shift, the 9 to 5, 11 to 7, 1 to 9, and our part-time shifts of 3 to 7 and 5 to 9. That's 4 hours each. All right. So right here, the solver that we used, the objective would be the total cost, which is the sum product of our daily cost per shift right here and the number of operators working those shifts. And we'd be at a minimum to keep a minimum cost. And the changing variables would be this number of operators working. And the constraints are the number of calls that we are able to take per period, which is greater than or equal to the average calls that we are able to receive per period. And we also added another constraint that would make this the number of operators working an integer, because we are talking about people, manpower. So from solving that, we are able to get these variables for the number of operators working. That's 7 operators working for the first shift from 7 to 3. That's 15, 10, 1, 4, and 2. At a total cost of $2,394.
To improve the call center's efficiency beyond staffing adjustments, the hospital should focus on better internal coordination, dynamic scheduling, language accessibility, and patient guidance. First, the study case highlights a lack of communication between departments, leading to confusion over referrals. If clinics share information more effectively, it could reduce unnecessary follow-up calls and improve patient experience. Second, since call volume fluctuates, the hospital should implement a dynamic scheduling system, adjusting shifts based on peak hours rather than a fixed schedule. This helps control labor costs while ensuring enough staff during busy periods. Next, 20% of calls come from Spanish-speaking patients, but hiring bilingual staff alone may not be enough and could be quite expensive. The hospital could introduce pre-written Spanish scripts or FAQs for English-speaking operators to assist with common requests. This way, calls can significantly reduce delays. Finally, many calls come from parents confused about the appointment system. If the hospital provides clearer instructions through online guides or printed manuals, it can help patients navigate scheduling more easily, reducing overall call volume.